Okay, students, let's go ahead and go through exam number 3 here. And as I've said before, go ahead and self-grade yourself, see how you did. Plus, learn from your mistakes here. But this will be an important one tonight to see how you did as we come to the end here. All right, so let's go ahead and go through the multiple choice first. Question number 1, it says, at the end of a pipe, and so we're going to have a pipe, and we'll keep reading. The fluid has a density of, has a pressure of, and it flows at a speed of through the pipe with a cross-sectional area of 4 square meters. At the other end of the pipe, the density and cross-section is the same. Now, that's an important statement here, as we'll see here in just a second. It says, but the fluid flows downhill and has a vertical drop of 10 meters. Assume the simple case of no viscosity. So this is Bernoulli's equation here. And in fact, I thought I would go ahead and kind of print these equations as we went along here, but this is straight out of chapter 12, equation 18, Bernoulli's principle, that says that at one end you've got the pressure, and then you've got the energy associated with its speed, and then you've got the energy associated with its height, so it's potential energy, kinetic energy, and pressure energy. Okay, and then it goes through the pipe and it gets to the other end. So we'll call this 1 and number 2. And because of conservation of energy, we should have the same total energy, although it might be in different forms. And that's kind of the main idea behind this equation and Bernoulli's idea here. Okay, and so we can say here that, okay, right here, the pressure here is 150 kilopascals. Now, there's a little subtlety that can be easily overlooked here, but the same cross-sectional area. Now, I guess I didn't print it on this sheet, but I know we need it back when we do the free response. Here it is. And so in the free response, so equation 12.4, there is a connection between the flow rate, the area, and the velocity. And so if the area doesn't change and the density doesn't change, that also means the velocity doesn't change. And that's going to make this problem then a lot easier, realizing that whatever the speed is at number 1, which they give us, but it's not needed, is the same at number 2. And so the energy associated with kinetic doesn't increase, doesn't decrease. Then, and depends where you call height 0, I'll just say this side of the pipe is 0. And my drawing's not very good because then it says it goes downhill. And so we're looking at what is the pressure on this end of the pipe. And so rho being the density and G being 9.8, and then a drop of 10 meters. So I'll say the final position is a negative 10. Obviously, you could have called that 0, and then this side would have been a plus 10. And mathematically, that's what you get when you bring it over to the other side. So, in other words, we lose gravitational potential energy. Therefore, it must gain pressure energy, so the total energy remains the same. Maybe I'll just put an equal, and then pressure 2 is what we're looking for. Here's the real math then. 1,500 times 9.8 times negative 10 gives me a negative 145,000 decrease. And so solving for pressure 2, bringing to the other side, I guess the thousands don't change. That makes a 7, that makes a 9, and that makes a 2. So 297 there. I guess that would be C if you wanted to describe it that way for number 1. Okay, so 297 kilopascals. And basically, the short answer is the pressure just increases by this little formula here. Okay, so number 2 says this. It says a pressure difference, delta P, of 2 Pascal dries a fluid with a viscosity of 1.25 Newton second per meter squared, which is also a Pascal second, which is our units for viscosity, through a round tube, and that's going to be important here, of radius 0.1, length 0.4, and what is the flow rate. And so, again, here is the formula, kind of the harder part of chapter 12. It's equation 12.45, but it's a straight plug and chug here. And so I'll put in a pressure difference of 2 and a pi and an area of 0.4 to the 4th power divided by 8. And this little eta is the viscosity, 1.25. And then the length at which it flows along the tube is 0.4. And so grabbing a calculator, it should be 2 times pi times 0.1 raised to the 4th power. That's the numerator. Divided by the 8, also divided by the viscosity, and also divided by the length. And 1.57 times 10 to the minus 4th cubic meters per second. And so there would be A for our second one on our harder fluid one. If you remember, chapter 2 had the easier fluid stuff. And so this is some of the harder stuff, I think, on the exam is right here because of the fact that we were doing the harder fluid stuff. All right, so number 3, in an ideal gas, its absolute temperature 400 Kelvin. What is the average kinetic energy? And so kinetic energy is the 3/2 Boltzmann's constant times temperature. It's chapter 13, equation number 55. And so I'll just kind of plug those in. 3 divided by 2 times Boltzmann's constant, which is 1.38 times 10 to the negative 23rd. And then 400 gives me 8.82 times 10 to the negative 21 joules of energy. So that would be D for number 3. Number 4 says a sample of gas at a pressure of, volume of, temperature of, how many molecules are there? And so what we call the ideal gas law equation, again out of chapter 13, has a connection between pressure, volume, number of molecules, Boltzmann's constant, and temperature. Sometimes we write that instead of number of molecules, the number of moles, which would change the constant from Boltzmann's constant to the ideal gas constant. And so whichever one seems to be the most appropriate, and since this one says the number of molecules, I think this is the more appropriate one. We'll just take pressure times volume divided by Boltzmann's constant and the temperature. And so the pressure is 100 pascals. The volume is 0.2. Then divide it by the Boltzmann's constant again. And then the temperature of 400. Now, and we come up with 3.6 times 10 to the 21. So it looks like 4 should be C there. Okay, good. All right, let's go on to number 5. I think this will go on to chapter 14, if I'm not mistaken. Suppose that 4.186 joules of heat flows into a 0.001 kilograms of material, causing its temperature to go up by 10 degrees. What is the specific heat? Well, in the start of chapter 14, so equation 14.2, we have this idea of the specific heat. It's defined as the Q, the heat added, divided by the mass, divided by the delta T. Now, one thing I'm not real crazy about in your author's book is here he uses the Q for heat, and back in chapter 5, he used the Q for the flow rate. And I guess there's just only so many letters you can use, and that is the common symbols, so I don't fault him on that, but when you list them like this on a formula sheet, it can look a little funny here. So this Q and this Q, which is out of the thermodynamic stuff, is all heat, whereas this Q is the flow rate from our fluid dynamics, and so that is the flow rate. Anyways, little subtlety there. But that being said, we can just punch these in, and maybe the trickier part of this is to watch our units, because they gave energy in joules, but the answer's in calories. They gave mass in kilograms, but the answer is in grams. Now, they did say Celsius, and so that matches fine. But I'm just going to be a quick conversion, and since this is the direct conversion, this is just 1 calorie. So mathematically, this is pretty easy, because this is exactly 1 gram also. And then it's just 10 degrees Celsius. And so 1 divided by 1 divided by 10 is just a 0.1. And so it'd be 0.1 calories per gram per each degree, which I guess would make it a C there for number 5. All right, so number 6, I think also from 14 here. It's our conductivity. Consider a steel plate, and so maybe I have a plate here, of a slab looking plate. Maybe it's real hot on this side of the plate and cold on this side of the plate, so energy is going to flow. And that's what it says here. Consider a plate 0.01 meters thick. And so this is the thickness, which in that chapter we've labeled the thickness as D, and has an area. And so this area where the heat is exposed to the temperature difference, on this side I've kind of drawn it cold, but there'd be just as much on the other side, the hot side. That would be an area A of 0.5. The thermal conductivity of the steel is 80. Keep that one in mind. If the temperature between the two faces is 200, so we really don't know what these values are, but I'll just say 0 degrees and 200 degrees, so there's a difference of 200 degrees, then what is the rate at which it flows? And so this is our next equation, equation 14.26, the flow rate, heat per time. Not, again, to be confused with the fluid flow rate, but this is the heat flow rate. So Q is the heat, so when you divide it by time, it's a flow rate. Okay, so we need the K, the thermal conductivity of it, that's the 80. Then we need the area, that's the 0.5. Then we need the temperature difference, that's the 200. And then we need the distance that the heat gets conducted. That's the D, that's the thickness of it. So that's the 0.01. And so grabbing my calculator here, I will go 80 times 0.5 times 200 divided by 0.01. And that looks like an 8 times 10 to the 5 and joules per second. So it looks like a B for number 6. Nice. All right, on to question number 7 here. And I guess this would be in chapter 16. It says, consider a body of mass m, 0.01 kilograms at the end of a spring with a spring constant of 0.1 newtons per meter. The body is set into simple harmonic motion by pulling the body 0.05 meters from the equilibrium position and releasing it. What is the maximum speed of the body as it oscillates? So this is our mass on the end of a spring, and its energy is made up partially of kinetic and partially of a stretched spring. And so this is this equation, 16.35. And it equals then a constant because this is the total energy, and energy is conserved going back to, I think that would be chapter 7. Okay. And so what you can do is you can say, okay, when you pull it all the way down and release it, you have a 0 kinetic energy, and you have a position, which is its full amplitude, which I think your book used a capital X for that. But I'm just going to put in a number, pulled down by 0.05 meters, and I will square it. And then, so as you release it and it goes back, that would again have to equal this same formula, conservation of energy. And it would, I'll put a plus sign here, but because it gets back to its equilibrium, it has 0 potential energy. And because it has 0 potential energy, that is where it has its most kinetic energy. So it's been accelerating back till it gets to equilibrium before it starts compressing the spring again. And that's perfect because that's what we want to find, this maximum. So this is a 1/2 times a 0.1 times a 0.05 squared. And then this is 1/2 times 0.01 times maximum speed squared. And I guess I can save myself a little bit of calculator work by canceling off the 1/2. And so I'd have a 0.1 times a 0.05 squared here. And if I divide that by 0.01, that would be the speed squared. And so if I take the square root of that, I guess I am looking at D for number 7. Okay. Number 8, I think also here in our waves, it says, suppose a wave has a wavelength of 0.1 and a period of what is its speed. So kind of the easy plug and chug one here is the idea of a velocity. It's distance divided by time. And so if you do one wavelength and a time of one period, you get this nice little formula, which is the wavelength divided by the period. And the reciprocal of that is a quarter, so it's a 4, and so that'd be 0.4. So 0.4 meters per second would be C. For what number is that? 8. Okay. On to question number 9 and chapter 17, and our last one for this semester before we get started with 18 for those of you who are continuing on. Okay, but that's next week, so we'll worry about that next Monday. Okay, let's see. Consider the speed of sound to be 343, so that's kind of the standard speed of sound in air at room temperature. A child a loud whistle that has a frequency of 2 kilohertz, but the child's riding in a car that's coming towards you, and you are not moving at a speed of 50 meters per second. What frequency do you hear? So this is the Doppler effect. This is, I think, one of the more interesting things of waves, and maybe a little more advanced part of it. But here's what we worked out in the sense that there would be what we would call the frequency of the real source, but what you observe has been affected by the speed of the wave and the source, where we use the minus sign when it's coming towards you. And so that's equation 17.20. So in my case, I'll take the 2 kilohertz for the original frequency. the speed of the wave right here is at 343, and then also put it here, 343. And we'll do the minus sign because it says the child that is coming towards you. And then this is the velocity of the source. And so this is the whistle, if you will, which is in the car with the child going 50 meters per second. So why don't I take the 343 and divide it by 343 and take 50 away from it. So that looks like about a 17% increase. So when I multiply by the 2, it bumps it up to 2,034 hertz, or 2.34 kilohertz, which would be D here for answer number 9. Okay, and then on to the last of the multiple choice here. This is about the sound level. It's a logarithmic scale here. And our sound level, measured in decibels, is the log base 10 of this ratio, where, well, let's go through the math. And so sound level beta in units of dBs would be 10 times the log. And so sound level has an intensity of, and they have 10 to the minus 9. And then there'll always be kind of a reference on these logarithmic scale, whether it be sound waves or the Richter scale with earthquake waves. A lot of electronics will do this. There's some kind of reference. And for sound waves, we like to use the minimal amount that a human ear can hear, or at least on average. And so that makes 10 times the log of... And with exponents, you move it, well, you subtract them when you divide. So this is going to be log, or it's going to be 10 to the third, and the log of that is going to be just a 3, and so that's going to be a 30. And so that must be C for number 10. Nice. So didn't need a calculator for that one. All right, so there's the multiple choice. Hope you did well on those. Let's move in then to the free response. And actually, maybe I'll keep this paper handy. I was going to toss it on my floor here, but I'll just do the backside here for A. Okay, so 11A, or 20 points. Yes, there, 20 points each. It says a fluid flows in a circular pipe of cross-sectional 0.2 meters. Pressure difference of the 2 points. And hopefully all this sounds familiar, because as we read all of this, without giving you the hint this time, we're back to our flow rate. And so this is the pressure difference, this is the pi, this is r to the 4th. Here is the 8, here is the viscosity, and here is the length. Okay, then it says what is the viscosity. So the viscosity is this little eta I'm looking for here. So maybe I'll write it that way. Here's eta. So this is going to be the pressure difference times pi r to the 4th. 8, and I'll just move the eta here and the flow rate down here. And that's why I printed this sheet, because I go, well, I'll just kind of list the formulas that we need. And there it is, the first one, again, this 12.45. But we're also going to use this 12.2, because one of the things that we need in this equation is the flow rate, which is area times velocity. And so if you look at this, it says it's a circular cross-section, has an area of 2, and somewhere it gives the flow rate, yeah, an average speed of 3. And so that number is a 6. So there's our flow rate. Now, some of the other numbers giving in here were the length of the pipe, 2 points separated by 1.33 meters. So there's the L, the length of the pipe. The pressure difference, or the pressure dropped. And so this would be, you know, of big concern as we, okay, well, how does the pressure drop as maybe blood moves through the veins for you life science, or maybe for you hydrolysis, how does the pressure drop down a main sewer, or not a sewer line, but a main water line, especially when it comes to fighting fires. Is this fire hydrant that we just built, that is extended out on the edge of town, what is that pressure drop? And is that going to give us enough pressure to fight a fire here, or do we have to do something more? Do we have to make the pipe bigger or whatever? But that's this idea. And so I'll call this a side calculation we need to do. But we got another side calculation because we need the radius. And since it says circular pipe, we know that area is pi r squared. And so the area is 2, and this will allow us to solve for r. And so if we move the pi to the other side of the equation and take the square roots, we get a radius of this pipe, it's a big pipe, 0.79, and it looks like I'm going to round it up to an 8. So 0.798 to the 4th power. So it looks like we've got two, what I'll call side calculations based on this information in order to feed it into the main equation here. And now we can finally get what is the viscosity given this pressure drop. And such a big pipe, that's a big pressure drop for a lot of pipes. So this is probably a thicker material than, say, water. Well, let's see what we get here. So let me go 25.5. I'll multiply that by pi. Then I'll multiply it by 798 raised to a power of 4. Maybe I'll just hit enter to get the numerator. Okay, so there's the numerator. So let me divide it by what's in the denominator, which is 8 times 6 times 1.33, close parentheses. Okay. And I get a, reasonably big viscosity. This would be like motor oil or something. Maybe not real thick oil. Certainly not thick like honey or molasses or syrup. But not a thin oil either, too. This wouldn't be like your cooking oil. This could be, a motor oil, probably a 40 weight, maybe a little higher, 50 weight, 60 weight oil. But anyways, it's got a reasonable amount of viscosity. Now, let me make sure I also finish with the correct units. These are, of course, in Pascal seconds. You can see that here when you put in your units. Here's the pressure, Pascal. Here would be the meters to the 4th power. We would then divide that by, no units to think about for the number 8. But right here, here's the flow rate. So here is a joule per second. And sorry, I was back to my same mistake, heat flow per rate. This is volume flow through rate, so this is cubic meters per second. And then this is the length into another meter. And so nicely, the 4 meters on top cancel with the 4 meters on the bottom. This, when we flip and multiply, bring it up, and so our units are the famous Pascal seconds I think mentioned on an earlier problem, and definitely was covered there in the book, especially this chapter 12. This was straight after. Okay, well, hoped that one helped somewhat. Let me grab another sheet that I tossed here on the floor. I guess this is back to question 7. Let's do B here together. So B says a volume of V, 0.02 cubic meters, of 8 times 10 to the 23rd atoms of a monoatomic ideal gas is under a pressure of 200 kilopascals. What is this average kinetic energy? And this is a lot like a multiple choice, but a little bit deeper because we got a side calculation here. And so we have this PV equals number of molecules, Boltzmann constant times temperature. Or we can write it as PV number of moles times the ideal gas constant times temperature, whichever one you prefer. And it looks like on my little printed sheet, I did this one and then this one. And these are the two that this problem involves. So 13.18 and 13.55 or 55. Because this one gives me, again, like the total number of molecules. So this would be a good step here. So the pressure is, let's see, what was it, 200. And we got to be careful there with our units, kilopascal. A volume of 0.02. Number of molecules or atoms, 8 times 10 to the 23rd. A Boltzmann's constant, 1.38 times 10 to the negative 23rd. And actually that's really nice because when you multiply exponents, you just add them together, and a 23 and a negative 23 added together give you 10 to the 0, and anything to a 0 power is 1. So those will go away. So that'll save me a little bit on my calculator. And then I'll get the temperature. So there's the first calculation, where I take the 1,000 times 0.02, maybe hit enter. I would divide that by an 8. I'd also move this over and divide it by 1.38. And so this is going to tell me I have a temperature of 362 Kelvin. Watching my units, because this is a joule per Kelvin for Boltzmann's constant, and that's why Pascal and cubic meters were important, not kilopascals, so that these two together would come out to be a joule. The joule on that side would cancel with the joule on that side, and the units would be a temperature on the Kelvin scale. A much more useful scale when it comes to understanding the physical motion, because only the Kelvin scale does motion and the value on the scale correlate. That's why we have a 0 motion with 0 Kelvin. Now that being said here, we're still after the average kinetic energy, and so this is that equation 13.55 that we saw on one of the multiple choice ones. But since the temperature is already in my calculator, let me start there. Boltzmann's constant is 1.38 times 10 to the negative 23. And then times a 3 and divide by a 2, working backwards. And I get a kinetic energy then of 7.50 times 10 to the minus 21 joules. And again, Boltzmann's constant is joules over Kelvin, like we mentioned here. So when I get a temperature in Kelvin, I multiply them together and get an answer in joules. Yay! Okay, so there is 11B. And then finally, 11C, and it might be the harder of the three, is got two parts to it. So let me grab another one of these papers I worked on about the backside of questions 3 and 4 here. Okay, so 11C says this, and we have a 1 meter long pipe that's open on both ends. Now that's going to be important. Also, it's at room temperature and it's in the air. And so this part here where it says room temperature and in the air tells me that the velocity is at 343 meters per second. Of course, we could throw that into the little formula here, but I kind of suspect that you know that one. We've done that one so many times here. At least I'm hoping you do. All right, so I'm going to keep that in mind. And the opened on both ends means that I'm going to go into chapter 17, and it's equation 1737 that says that these opened in pipes can make a frequency that depends on their length and the velocity of the wave. And then there's this n factor, which can be any integer. So there's a lot of different frequencies. But that's where it's right here. If the pipe is struck with a hammer, what is the fundamental? So the fundamental is the lowest one. And so that is the giveaway sign that n is equal to 1 for this problem. And as I mentioned earlier, the velocity of the wave was kind of given indirectly also. And so both the n and the velocity of the waves are given indirectly here. And in this case, the length is 1 meter. It's going to get more complicated when we cut it. But right now, it's just 1 meter long. And that's going to give me my fundamental frequency. And so it looks like it's just the 343 divided by 2, which is a 171.5 hertz. So there's the first part, and hopefully pretty straightforward part. Here's where it gets a little harder, both conceptually and definitely mathematically. But here, the pipe is cut into a short piece and a long piece. So let's call the short piece L1. Well, how about LS for short? And LL for long. But one of the things that I just want to emphasize is you're going to cut it. The two lengths now are going to add up to 1 meter. And so that's an important piece of information here. Now, with that being said, we do then have, like in part A, it's just now we have two pieces of pipe that are open on both ends that will then follow the same type of pattern. And so you might say we have one of them, which is L for the short pipe. So I'll say the frequency for the short pipe for a given N. And we have also the frequency for the long pipe. Now, I'm probably wasting my time writing these ends here because as you read the problem here, it says a pipe is cut into a short piece and a long piece. The two pieces are used as a wind chime that have a beat frequency of 57 hertz. Use the fundamental frequency. So in other words, use n equaling 1. So I'll just write this. The frequency of the short one would be the velocity of the wave, which I'll just write as 343 over 2ls. And the frequency of the longer piece would be 343 divided by 2L of the longer piece. Okay? And the idea of the beat frequency is really the difference between these two. Now, since the L is in the denominator, the shorter one's going to have a higher frequency. So Fs minus Fl should be 57. I guess we could have written that as Fl minus Fs is a negative 57. And I suppose we could even, well, just ignore that and do absolute values, but then the short piece is just going to be the long piece. And yeah, so, and like any absolute value, there'll be two answers, and the long piece will become the short piece. Anyway, so it just, I guess what I'm trying to say is, if you cut it, say here's the middle, if you solve it without the absolute value, you'll call that the short piece. If you then put in the absolute value, you'll get that piece. But either way, this will be the short piece, and that'll be the short piece, and it'll be the whatever length. So because of that, I'm just not even going to put the absolute values or worry about this minus sign here. I'm just going to put this. And then take advantage of this. So this is 343 over 2 LS minus 343 over 2 LL equals 57. And so maybe I'll put a little box around here, but here's where the math's going to get a little harder, is because I now have a system of equations, two equations and two unknowns. I've got the short length and the long length based upon the beat frequency, but I also got the short length and the long length based upon the total length of the original pipe before you cut it in half. And of course, you remember from your math class, you got two unknowns, you're going to need two equations. And so that's why I wrote that one down first. Don't forget that piece of information, because if you just kind of followed the physics part, you might end up here and kind of forget about the original length of it. But I'm going to need these two. In fact, why don't I just grab another piece of paper here, and I'll start doing my equations, although maybe I'll simplify this a little bit first. Each of these has a 343 and a 2 in it. And so I'm going to factor that out. I guess I'll also imagine moving the 2 upstairs and the 343 downstairs. So 1 over LS minus 1 over LL is equal to, and I'll grab the calculator here. And so I got 57 times 2 divided by 343. And so this is going to be a 0.332. And so that'll be a little bit easier equation as I head into the math step here. Okay, so let me get another piece of paper here. So my first equation is this LS plus LL equals 1. And the second is 1 over LS minus 1 over LL is equal to 0.332. So there's my system of equations. And the question says, what is the length of the shorter one? So let's be strategic here and get an equation for the shorter one. And I'll do that by first taking the first equation and get an equation for the longer one and put it into the second one. And that means I will have an equation that only has the shorter one left over. And that's what I mean by strategic. Let's end up by combining these two equations. I'm going to have one that only has the LS, the shorter one in it. Okay, so with that in mind, we still got quite a bit of algebra to do because this denominator thing makes it a little more challenging. So, like all fractions, you need a common denominator. And so I'll just multiply the two to get a common denominator. And since this one already has an LS in it, that means that I had to multiply this one, top and bottom, by 1 minus LS. And this one here already had the 1 minus LS, so I had to multiply the bottom by LS, which means I have to multiply by the top by LS. And so this top just becomes 1 minus 2 LS. And the bottom becomes an LS minus an LS squared equals 0.332. And sadly, again, got some more math here to do because this is a quadratic equation. So I'm going to have to move this to the other side. So this would be LS minus LS squared. And I bring it over. And so I get 1 minus 2 LS. And then when I distribute this, this is 0.332 LS minus 0.332 LS squared. And so you can see I have some LS's that need to be combined together. I have a quadratic term and a constant term. Why don't I just bring this over so it becomes plus 0.332 LS squared. When I bring this over, it becomes a minus with that minus 2, makes minus 2.332 LS. Then I have the plus 1, and that equals 0. So, again, quadratic formula here, or a quadratic equation can be solved with the quadratic formula. So that says take the opposite of b. So b is a negative 2.332. So I'll put a plus 2.333. Plus or minus the square root of b squared, 2.332 squared, minus 4 times a times c all over 2a. And so here is the plus 2.332 plus or minus. And here's where I'm going to need to grab a calculator here. And so 2.332 squared minus 4 times 0.332 times 1. And then take the square root of all of that. And so this is 2.03. And this just would be a 664 with a decimal there. Okay. And it looks like the extraneous root is going to get when I add them together, because that's going to be way over 1. And clearly, when you cut it, it's got to be something less than 1. And so I guess the correct one would be with the minus sign. But I'll just work out both. 2.332, and I'll do the plus sign first. And divide it by 0.664. So there's the extraneous root 1. We can ignore that one. So cross it out. And here's the significant one, the minus sign. So 2.332 minus 2.03. Then divide by 0.664. And that is 0.455 meters. Which, out of curiosity, means that 0.5 4, 5 meters is the long one. But the question asks for the short one. So there's the short length and there's the long length. So a lot of algebra in that one. Hopefully that didn't mess you up here, but quadratic and, like I said, a little challenge with conceptually and mathematically. So I guess I would say again, I think this 11C, and particularly part B, is the hardest of these free response. All right, well, hope you did well on that, and I hope the little video here was helpful and gave you an idea of what your score is, as well as what mistakes you made, so that you won't make them again and you'll be that much more educated. All right, take care.